And let's go now with the next presentation by José Capmany from the Universitat Politècnica de València. The title for the presentation is Photonics Field Programmable Gate Arrays.
Sí, ahí. Está aquí. Ahí. Ahí, sí. No debe... Ah, bueno, no sé si lo había puesto. Ahí lo tienes. Tienes el pasador ahí. Vale. Okay. All right. Good morning to everybody. Thank you very much to the organizers for inviting me. And I'm going to take the chance of trying to introduce you a novel concept that we are developing here in Valencia, and both at the research group and at the new spin-off company, which is the Photonic Field Programmable Gate Array. All right, today my index for it's quite a short one. I'll give a brief introduction and try to recall some concepts about programmable reconfigurable systems in electronics, which have made this technology so successful. And we'll try to see what are the evolution steps, because there's definitely like a parallel development in photonics, at least from our point of view. And then we will see why this approach has worked fine so far, but probably will need to resort to other complementary technologies. I think that previous speaker has also mentioned that there are some limitations that are being reached today, for example, regarding Moore's law and the fact that it's not so cost-effective to go down in integration scales nowadays. And for that, one of the solutions that we advocate for is to use integrated photonics and more particularly programmable photonics. So I will spend some time in trying to give some overview about what have been so far the main achievements in programmable photonics, and of course there's an evolution path which resembles quite a lot to that of electronics. And of course, one of the natural conclusions is that why not going to try to do some device that is similar to the field programmable gate array in electronics. So that's going to be the third part of my talk, and then I will conclude that with some summary and conclusions. The third part on FPGAs is going to be the core of the presentation. I don't know if I will have a lot of time to cover most of the aspects, because it's a real complex problem and environment to take into account. But I hope to be able to convey the message and the most important things that have to be taken into account as well. All right, so let's go into the presentation then. The introduction. Well, this presentation is about reconfigurability and reusability, and in fact, it's an approach, holistic approach, not only of TIC systems, but in any technology, the ability to reuse resources means that you are able to save costs, and this is, well, probably this is a very unrelated to information systems example, but it shows you that the reusability can be incorporated into even large-scale or large-size technologies. In this case, is the project that SpaceX has to be able to reuse the rockets to reduce the costs by a significant amount in the cost of putting or materials or men into space. Right, but this concept, we are quite familiar with that, because in electronics, in a more close example to information technologies, in electronics we have FPGAs, as you know very well, field programmable gate arrays, that have replaced in some application fields and in some contexts application-specific circuits. Even in networks, we now, it's more common to speak about software-defined networks, where you have, rather than ad hoc network topologies and software-defined networks, you have a set of resources, and then by suitable programming, you tailor that network to your needs, and you're able to dynamically change the configurations. In radio, of course, we have the software radio as well, and we could go and further and provide more examples. But I'm going to try to focus on electronics, because it's something that is quite known to us. Well, from electronics, in electronics, so just very briefly, we all know most of these achievements. After the invention of the transistor, which was a completely discrete device, the next step was to trying to get something more integrated. So the first integrated electronic circuits were proposed by the end of the 50s. And from that on, we had a period where application-specific circuits dominated all the electronic landscape, and more or less specific, of course. And from that, it was around the end of the 60s, the beginning of the first proposals for memory-specific chips, even first microprocessors. But then, actually, one of these inventors in electronics, Bob Noyce, at the end of the 60s, was worried about the fact that there was a big proliferation of different integrated circuits. And I took out this site from this nice book about something that Bob Noyce said about this ASIC proliferation, and that it would be at that time he proposed the fact that there should be an evolution to general purpose chips. The main reason is that they could be manufactured in huge amounts, benefiting from economies of scales, and that they could be adapted for specific applications by using programming. Okay, so actually this is we had to wait. Even though the microprocessor was proposed and fabricated in the early 70s, we had to wait until the late 80s for this similar, like fully programmable device to be proposed. And this is a copy of the patent application for FPGA. I like to put the title because it's quite self-explanatory. A configurable electrical circuits having configurable elements and configurable interconnects. So that's the main rationale behind FPGAs. Everything is reconfigurable. It's digital, it's reconfigurable, logic elements which can be configured. They are made of digital logic gates, and the connections can also be configured. Right, so yeah. That's basically the core of the FPGAs, digital electronics. The configurable logic elements are made by hundreds of different digital gates, which are irreversible, 2 by 1. That means that you cannot get the output, the input from the output, but of course you don't care if you're playing with digital electronics, which is what FPGAs use. They use digital signals and Boolean algebra. Okay, that's just to remember, and they have been absolutely successful. I mean, they have replaced many in many applications the application-specific circuits because they bring a lot of advantages, and I would like to focus on specifically on two of them. The fact that they are very competitive in terms of non-recurring engineering costs. That means the cost that you have to incur every time you design a new application-specific circuit, and flexibility. Okay, so if you have a look here through the years, this is a little bit of the evolution of electronics from the transistor to programmable. Okay, about 40 years before we had first FPGA proposals, patents, and nowadays we have like a combined ecosystems where both programmable and application specific circuits coexist. Right, but there's a problem at site, and you know that we have been able to shrink the size of transistors for many years. The more well-known Moore's law is not holding any longer, or at least started to cease to hold. And at the same time, some applications are emerging which might need non-traditional computing approaches. And my fellow speaker, preceding one, Bert has already mentioned that this might happen with neural networks. Okay. But it's not only neural networks, it's also quantum computing, maybe also 5G, because we need analog signals, etc. So maybe we will be in a situation in a few years where electronics is not enough to cope with the processing speeds and needs to team up with other technologies to meet the requirements. And for that, of course, photonics is an option. Okay, and again, in photonics, we have these two paradigms that we can as well contemplate. Like in electronics, we have application-specific integrated circuits, which most certainly both of you, all of you are familiar with. But we think that the time for programmable photonics is approaching, probably has already come, and it would be interesting to anticipate similar solutions to those of electronics, okay, in particular FPGAs. So, programmable photonics. What is programmable photonics? And first of all, let me go again about and give you a little bit of history, just to put it on context. We here are most of us working on integrated photonics, and in many presentations you go to the conferences and you find this this paper as being quoted as the beginning of integrated optics. Is a 1969 paper by Stewart Miller from Bell Labs, and where the first discrete components, waveguides, rings, etc. were proposed. And of course, we have, after that, there's been an explosion of work on different components, active, passive, and mainly the activity has been on application specific. And of course, there's been a lot of work, but since the 2000, more or less, there have been companies being set up, and of course new ones, and also let's say incumbent ones, which have been working on application-specific, high-performance application-specific circuits, specifically for transceiver applications. Nowadays, for data center applications, this is the kind of aspects that have been, I would say, more developed within all the ecosystem. Well, yeah. In aspects, what we have, and I want to stress this from the photonics point of view, is the same problems as with ASICs in electronics, though the time scales are much longer and the costs are much higher. For example, when you design an ASPIC, you have a problem to solve, you have an idea, you have to make your tentative designs. That takes mainly about 3 to 4 months, if you're lucky. Learn the CAD software if you don't know it, study PDKs from the selected foundries, then go for fabrication. And that fabrication can be, that is a very over-optimistic, probably from 7 to 12 months. Sometimes it's even more, okay? When fabrication finishes, then you have packaging, okay? And then you have testing. And in the test, everything can go okay, but you may have problems. So at the end of the day, you have something that in around 12 to 24 months, a budget that can be over 200,000 Ks if you go for a dedicated run, of course. And nothing guarantees you that everything is going to work. So if something fails, okay, you have to start to have iteration loops in the design procedure. So if you could find a solution where you could avoid some of these cycles, both in terms of time and cost, that would certainly be something of interest, and this is where programmable photonics comes. Well, just to give you a very short overview of the evolution in programmable photonics, we've been, during the last 10 to 12 years, going from what we call reconfigurable aspects, which are not really programmable circuits in the wide sense. I mean, there are really application-specific circuits in which you can tailor the value of several components, but your architecture is fixed, and the range of things that you can do is very limited. For example, a filter, okay? From that, we went through what we call few functional aspects. That means these are aspects which are a little bit complex, and they are designed so they can do 2 or 3 things, not with the same quality. For example, this structure here is designed to be a filter, but you can program it a little bit to perform like a Hilbert transformation or something like that, differentiation, integration tasks, but not with the same degree of quality. At the same time, we have seen people working the emergence of integrated optics technology for quantum computation, and in particular for linear optic transformations that are required in quantum computing. For doing that, what you need is to have a very good matrix multiplier, like in neural networks or in artificial intelligence, and that has been done using multi-port interferometers, integrated interferometers with different varieties. You have rectangular or you have triangular configurations, right? These are feed-forward only structures. That means that, like in my previous talk, that would be, these structures would be okay for deep learning feed-forward structures, but they cannot provide recirculation. They cannot provide feedback. So the next step has been the proposal of what we call waveguide meshes. In this case, what we have is something similar to a multi-port interferometer, but in this case, the basic unit, which is a Mach-Zehnder interferometer, is connected in such a way that recirculations are enabled, and you can connect them in different ways. This shows an hexagonal topology, but of course, certainly you can use other topologies like the triangular or the square ones. Now, this is actually a quite powerful device that can provide not only these feed-forward only operations, but also can do any kind of feed backward operation as well, and a mixture of both. So the next and in our opinion more interesting thing to do is try to use this as a core, photonic core of a much more powerful device that resembles very much the field programmable gate array. So that's the core surrounded by different elements, which I will explain in a few minutes. So just for comparison, okay? This is the evolution of integrated electronics, evolution of integrated photonics. They are similar, they are not the same. We hear this every now and then in all the conferences. Integrated photonics is following the same path as, well, yes and no. In a way, it's similar because the main concepts are similar, but the time scales are different. But if you have a look at this, this diagram, yeah, we see that from the most, let's say the standalone devices that were first proposed in the late 60s till the moment where we are thinking about having programmable and FPGA type devices, the lapse of time is, well, a little bit higher than in the electronics, but it's not so different. And the evolution steps, I mean, which kind of circuits and which kind of functionalities have been through over the evolution it's similar, okay? So it might be a right time to think about this kind of programmable devices. In our case, what we bet for, or what we think is the most adequate device is the FPGA, the optical FPGA, or photonic, in our case, field programmable photonic gate array. And I keep all the words because all the words are meaningful, okay? So this is more or less an illustration, figurative illustration of what we intend by a field programmable photonic gate array. We have a photonic core, photonic part, here, which is made by a photonic core implemented by a waveguide mesh, some external high-performance blocks, which actually will be specialized circuits, much in the same way as we have high-performance blocks in electronic FPGAs, and then input-output ports. And what we will have in addition to operate this, we need some electronics to control and to monitor, control, program, and do several tasks, which I will comment in a few minutes. And then we have a software layer to operate everything. Okay, so this is more or less the layer stack for this device. All right. Okay, so I'm going to first talk a little bit on the hardware layer, on the hardware tier. Right. When we say that FPGA is an array of gates, we mean something similar but not exactly the same as in electronics. All right. The core of FPGA, as we see it, is a 2D mesh of interconnected 2x2 unitary and reversible gates. That's the difference with electronics. We are going to use reversible gates because we are going to work with analog signals. Our variables are not current or voltages, our variables are amplitude and phase, okay? So FPGAs are going to work with analog lightweight signals, and they are going to be based on gates that implement very simple 2x2 unitary transformations, like the ones, for example, people use in quantum communications, right? That's the first thing. How can we implement these gates? Well, it turns out that nature has been, in this case, kind with photonics, all right? Reversible gates are implemented. I'm going to use a little bit of mathematics now, but you don't need to fix it, to follow the details. Just the conclusions, okay? As I said, well, reversible gates are used, can be built by using transforming a mathematical object that we call polymatrices that again are used in quantum communications. It turns out that what we are actually doing is using the things that people are considering for quantum communications or quantum computing. We are going to try to use them for classical operations, right? So actually these are the 4 basic matrices, and the transformations that we need to do to implement the gates are called rotations. Very basically, the rotations are operations of these matrices, but it turns out that there are 3 kinds of rotations around the x, y, and z. And I said that nature has been generous with photonics because it turns out that you can implement these rotations with tunable couplers, with 3 dB Mach Zehnders, and with phase shifters. At the end of the day, the basic elements in all these 3 configurations is the phase shifter, which is actually, for analog processing, the equivalent to the transistor, more or less. It's not the same. It doesn't work in the same way, but it's the equivalent in the sense that it's a very basic component. With these rotations, it turns out that you can do any unitary operation. If you do a cascade of rotations, and you may wonder, okay, this is extremely complex. We are transforming matrices, and then we are using rotations. We are cascading rotations. And again, this seems very complex, but it turns out that it is not, because you can do any unitary arbitrary 2x2 rotations, either by cascading y and z rotations or x and z rotations. Turns out that this first configuration is a 3 dB Mach Zehnder interferometer, and this one here is a tunable coupler, is a directional coupler, sorry. So if you are able to access these phase shifters, then you are able to program, then you are able to do any kind of 2x2 gate. And this is very important, because with 2x2 gates you can do anything. You can do any unitary matrix transformation. That's a very, very, very old result from even from, I think it's from 19th century, okay? But you can do any feed backward as well architecture. Impulse, infinite, finite, and mixed structures can be implemented if you are able to use, if you have a structure where you have your 2-dimensional interconnection of unitary gates. You can then connect them in many ways, and it turns out that there is an isomorphism between the way that you can connect these gates and the architectures, the physical architectures of the main waveguide meshes, the square, the triangular, and the hexagonal. And this is what has been physically reported in several papers over the last years. We've seen demonstrations with these meshes with quite modest number of elements so far, okay? These are like 2, this is like, let's say, 7 hexagons, this is a little bit more, 2 triangles, etc. But these are just proof of concepts. The next generation will integrate around 80 to 100 cells and over several hundreds of phase shifters. The idea is that any kind of this element is either a directional coupler, tunable directional coupler, or a Mach Zehnder, tunable Mach Zehnder interferometer. So with that, you can, of course, have the core of your device. And then what you append, what you use as external high-performance block is up to the application. This is not very different from what you have on FPGAs today. In FPGAs today, you buy a basic core and you're able to specify which external high-performance blocks you want. And in photonics, you can think about many alternatives, like delay. You want to add specific delay lines, dispersive elements, sources and amplifiers because you want to compensate losses, or, for example, because you want to do activation functions for a neural network. Okay, you want to use SOA bank or whatever, modulators, etc. So that's your hardware. Okay. The electronic tire, that's a different story. FPGA will not work only with your photonic hardware. You need also to have an electronic hardware, and this is going to be in charge of several very important tasks, like monitoring your readouts from the chip. And with this monitorization, you would like to do things like running configuration algorithms. You want to program your device because you want to act over your phase shifters, either electronically or with other control signals, driving the actuators, as I said, sorry. And actually, this is going to cooperate with your photonic hardware. And for that, you need three main elements. You need a processing unit that is going to be in charge of configuring and set the signals to drive the circuit. You need a monitoring stage that is going to receive the signals from the processing unit and will drive actually the elements, the driving, sorry. And you're going to have a monitoring array that is going to is going to get the information from your optical outputs in your FPGA and then pass it to the processing unit for further processing. Okay, so that's more or less the scheme. Okay. Finally, I'm going to spend some time talking about what we think is the most important layer of all, which is the software software layer. There we have two things. This is the software layer that is more connected to the driving and the monitoring and extraction of the readouts of the information that is required to set the to control and monitor the performance of the FPGA. And then you have a high-level layer, and this is going to be in charge of different aspects that are, again, used in electronic FPGAs. For electronic FPGAs, you need to be able to program, okay? You need a calibration, constant calibration of your device. You need to be able to program your circuits. You need to be able to specify where you want your circuit to be programmed in the available real estate of your hardware. You need to be able to correct unexpected failures. For example, if you have a program circuit and some phase shifter fails, and the system must be able to do self-healing, okay, and find another route to implement the same circuit. If you need to implement two circuits at the same time or three circuits, the software needs to be able to identify where is the best place to position each different circuit, for example. So there are two ways to do this. One is either using a software that is based on what we call global algorithms and presets. For that, you need to measure actually the circuit and store your data and then use it as a calibration or as a previous information to run all these algorithms. And these algorithms will be the ones that I mentioned before, but it can also contemplate like auto-routing, where to do. You have different paths to implement a circuit, which is the best. Okay? So that needs the knowledge of this preset configuration, so you need to be able to be continuously monitoring and or stopping in several cycles your circuit and gather this data. And the second alternative is use programming the software based on computational optimization algorithms. That in this case, this is especially good for devices where we aim to scale to a very high number of phase shifters and actuators. You don't need any prior knowledge of the circuit. You don't need any prior knowledge of the status of the circuit. What you do is you specify a performance that you want, and this is done by, as I showed you before, there is a waveguide mesh. You need to be able to compute something that characterizes the whole waveguide mesh, that is a complete scattering matrix, and this can be done almost instantaneously if you have the correct method. So then you compare your results with your target and apply a given optimization technique, which can be based on machine learning algorithms, a particle swarm, or whatever, and that will help you to evolve the circuit. Just to give you a couple of examples, well, this is how the system would cooperate. It's just a cartoon, but it's a little bit complex. But let me show you one example. One example is an experimental result on our very simple waveguide mesh, where we wanted to do some configuration, sequential configuration. Okay, so we want, first of all, we don't know what is the status of the waveguide mesh. It's been fabricated, so we don't know if your phase shifters are not biased. Then you don't know where the tunable units, the Mach senders, are either in cross, bar, or intermediate state. You need to know that in advance. After you know that, you know the initial state, you want first of all to program a very simple ring cavity, okay, with two 12-unit lengths. Then you want to evolve to a Mach sender configuration, and then you want to evolve to a simple structure where you have two circuits in parallel, a Mach sender and a ring cavity. For that, what you need to know, you need to have the vectors that give you the status of all the phase shifters in the whole structure. Okay, and the initial state, and then you need to know what is the state to which you want to converge and apply the correction and then evolve. So this is what I'm going to show you is an experimental result. We go from the first configuration, and we are expecting to have the filter at port 24 and port 12. Okay, so we see. We configure the ring cavity. Once this is configured, then we reset it, and we go for a Mach sender. So that's the output. And then when that is done, we want to reset the circuit and again program, and you will see the traces corresponding to a ring and to a Mach sender. So okay, you can do it with more circuits. You can certainly do more complex structures if you have more complex meshes. With the optimization algorithms, what we actually do, as I said before, is we extract the information from the circuit, from the different output ports of the circuit. We trade it off with our expected scattering matrix, and we apply a cost function, and we act over a vector that drives the whole system. The idea is that the cost function must decrease with time, and this is a specific example for a 1 × 8 star coupler that is implemented here. The idea is that as we proceed in the iterations, the cost function is reduced. The significant input-output port configuration converts to a 1 / 8, The rest, the non-relevant ports, should go to low values, etc. All right. But you can do this. This is a very simple example, and I'm going to show you a result that it's not yet published, but this is a little bit more complex and I think a little bit more exciting, which is what we call filters a la carte. That means that you specify in your software a mask, a spectral mask for the filter that you want, and that includes parameters like what is the ripple you want to have in your bandpass, what is your period, what is your contrast ratio, and then of course that implies a given scattering matrix. And what you do is you let the circuit learn and adapt itself to reproduce these different filtering characteristics. This is I'm sorry I cannot show you more results. This is an evolution of different kind of filters that we have been able to program using the same input-output pair. So we don't need to go to different parts of the circuit. It's just an input-output, given input-output configuration. You change the resources on your waveguide mesh, and you definitely have filters with different characteristics, different ripples, different periods, okay, etc. And with that you can do, of course, many other things. Of course, the last thing to comment is that for doing that, it's not only necessary to have a good software, you need a very good or an adequate equivalence to a specification language in FPGAs that needs also to be developed. So actually the photonic FPGA programming can be done by somebody who is not aware of the internal details of your device. Okay, so that's a good picture. What are the limitations? What are the challenges? Well, we have hardware and software challenges. First, power consumption. There, of course, if we need to increase complexity, we need to increase the number of cells, we need to increase the number of phase shifters. The phase shifters that we use today are thermo-optics, so they have a huge power consumption. They will not be good for that. So we have to look for other alternative mechanisms, even non-volatile, but that's something where people are working at the time. Of course, accumulated losses. The more phase shifters that you traverse, and if you're doing, for example, your FPGA on silicon, silicon is a passive device, it's a passive technology, you start losing power, you need to recover that. You may want to contemplate the possibility of having amplifiers somewhere, certainly not inside the waveguide mesh, okay, to avoid lacing effects, but probably as a high performance element. So we estimate that we might be able to integrate like 400 to 500 phase shifters in the near term, okay, maybe over 1,000 in the middle term. The electrical interfacing, of course, and system integration is a challenge from the hardware point of view, because you need to connect, you need to have a wiring to high density wiring to many elements. The monitoring points, where, how many, and also managing the optical and thermal crosstalk. And well, but we are working on ways to mitigate that. Okay. Software, well, there are certainly many challenges, but of course, managing of such a huge number of variables is is a very, very challenging aspect that will require, of course, these automated solutions, and probably to resort more to optimization rather than to preset or pre-characterization techniques. How fast we can reconfigure the FPGA is also a challenge, though it might not be a real need to do a very, very fast update. And of course, the fact that once you have fabricated your hardware, the behavior of your phase shifters, your couplers, etc., will be everything but ideal. So you have to be able to get this information and to compensate for them. Applications, of course, as you might think, there are many. There are many emerging trends where we see this specific system being applicable, but most probably for fiber wireless, hardware acceleration, and probably neuromorphic and quantum computing. Are the ones that come first to our mind. Although you cannot discard the fact that in a few years you might need smart coherent transceivers for coherent, and you may need to take back again some of the functionalities that you do on your DSPs back to optics, because it's faster, and then you unlock a little bit the capacity of your electronic hardware. Right. So summary and conclusions. I hope to have convinced you that programmable photonics is an emerging approach which is of interest, and because it will enable flexible, versatile solutions that cooperate with electronics. But in particular, from a point of view, is the field programmable gate array, the device that we see more competitive in many aspects, and however, we have to fulfill and address many challenges. So just to take home messages, programmable photonics is going to happen, yes or yes. It's not because I say it, it's going to happen, okay? And of course, it shares many commonalities with integrated electronics, but it's completely different. That's something that you have also to take into account. So I want to close saying that in a few weeks, there will be a first textbook on programmable integrated photonics. So that will be very, very soon. And also, I will take the opportunity to thank my colleagues from Micronics and from the Universitat Politècnica de Valencia for their kind assistance and help. So thank you very much.
Thank you, José. Any questions for José Capmany?
There's one there.
Yeah? Okay, David.
Hi, José. Thank you very much for a nice presentation. I have a question for you. In your view, what is the promising or the most promising material platform for implementing your FPGAs?
Well, that's a good question. So I would say that for the core, I would use a passive one, of course, a silicon or silicon nitride. But unless you consider an application for quantum communications which precludes the use of active elements, I think that the most suitable solution would be to have some hybrid or heterogeneous integration solution. And you can think, of course, of putting everything into the main core, or exploiting the fact that as we see the FPGA will have external high performance blocks, and then use your actives there. So I would say If you ask me, the hybrid technology solution is the best one. I don't want to commit on the passive technology because I know the people here working on silicon photonics and silicon nitride, so I want to remain neutral on that.
More questions? Don't be shy.
Yes.
So you're, at least what I was seeing, the same thing with the previous presentation, is that there's a lot of converting back to electronic signals and then onto photonic signals again.
Absolutely.
I see a lot of inefficiencies there. Isn't it possible also to have these programmable gate arrays that you have, just link them together just photonically without the translating back to electronics and then onto photonics again?
Okay. Well, right. Now, I'm probably this is a mistake I made. All the processing is optical, from input to output. Electronics is only required to program the settings, and to control. Okay. There is no conversion to electronics of the processed signal. Okay, the processing is all optics.
Okay, but I'm just wondering, isn't it also possible to have some kind of high performance interlink between different photonic FPGAs?
Yeah.
To just link them together photonically without even having to go.
Yes, and I think that Bert also said the same in the last. You can, of course, have more than one core, and you can interlink them optically, not electronically. You wouldn't need to, but you need to be sure that what each optical core is doing is what you want to do, and to do that you need electronics. Only for supervision and for programming. But the real processing is on the fly. It's on the fly photonic processing. You might traverse only one core, or your signal might traverse different cores. It might be a multi-core architecture. I didn't speak of that today, but it could be. But then again, you would need each core to be controlled. Yeah.
Thank you very much.
You're welcome.
Okay, more questions for José?
Hi, José.
Hi, hello.
Thank you for your presentation. My question is that can we expect that all that control and programming information, can we transform all of that into photonics also?
No, I don't see it. And my impression is that if you want to do that, you need to be able to do. I'm not saying it's not theoretically possible, okay? But from the practical point of view, if you want to extract information from an optical signal all optically, then you need to do extra processing of that signal, which would either be analog, so you would require extra filters, etc. But then you don't have access to that information, or it must be digital, and optics for digital is not very good. Okay, you don't have the equivalent to to the memories, to bistables, to threshold, yeah, but it probably the overhead from the controlling would be huge, even if you would be able to do it. I don't want to say no, but my experience after 30 years working, almost 35 years working in photonics, is that opticals pure optical signal processing with very few electronics has not yielded any industrial or a commercial solution that can be scaled. That's my opinion. Sorry, I'm not.
Okay, thank you.
Any other question? Okay, no more. And congratulations, José and your team for getting this milestone of creating Hyperonics. Lots of experiments and prototypes developed. The market is huge. Which is the field of the market that you would like to approach first? Do you have in your mind some approach for the next steps with Hyperonics?
Well, actually, in this case, what you usually, what we aim to do is to, first of all, you develop your beta prototypes. And with the beta prototypes, you will need to go to different players and say, okay,
To test.
you can use that, give them feedback. But honestly speaking, the way that we conceive this is as a general product, so we are not biased toward any application field, but all at the same time. So.
As it is. Thank you. Thank you very much.
You're welcome.
Then let's go now for the coffee break. Our brains need sugar.